Good morning, everyone. Welcome to the Ocean Best Practices session on climate downscaling to the coastal ocean. We've got over 100 people expected to join the webinar today. So we'll give people a few minutes to arrive. As we do that, I guess I can just introduce myself. I'm Jason Holt from the National Oceanography Centre, and I will be facilitating this webinar today. Georgia and Clotilda, do you want to quickly introduce yourselves while people are joining?
Sure. Good morning or good evening, everybody. This is Georgia Verri from CMCC Foundation. So I'm a researcher at CMCC Institute, and with my colleagues, we are among the activities. We are working on the limited area climate downscaling, reaching very high resolution and using an integrated modeling approach that I will show you later.
Brilliant, thanks. And Clotilda? You're muted.
Very good. There we go. Hi, everybody. I'm Clotilde Langlais, and I'm calling from Australia in Hobart. I'm a scientist at CSIRO in a coastal environmental modeling team, so looking at all the coastal seas around Australia. And we're starting to look into climate downscaling and talk about methodology today.
Brilliant, thanks very much. Also on the call we have Anna Catafuta, who's going to be rapporteuring our discussion sessions that we have after this. So welcome Anna as well. Although we can't see you, I don't know whether we need to. You could be made a panelist so we can see you, but I'll leave that to Katrina to sort out. Anyway, I'll get going with an introduction presentation. So I share my screen.
Hello, sorry, yeah, I joined as a panelist now, so you can see me.
Thanks, Anna, welcome. Right, can people see my presentation?
Yes.
Yeah, brilliant. Okay, so I'll get going then. Okay, so this is a session on best practice in climate downscaling to the global coastal ocean. So we have two sessions on this. We've got this one this morning, and then Thursday evening we have a second session. So those are really keen on this. So I'll give a quick introduction to the question of downscaling climate change to the coastal ocean. And then we have two case study presentations, one on the Adriatic and one on the Great Barrier Reef by Georgia and Clotilda. Then we have a 45 minutes for a moderated discussion, some questions that we'll be introducing for that. And we'll be done by 10 o'clock sharp. We have a hard cut-off time then. Okay, so just to introduce the issue here. So basically that we need to be able to provide actionable information about future climate impacts in the coastal ocean. And blue economies and coastal communities requires this information around emerging potential climate change to plan and adapt. So climate impacts can generally be grouped into maybe three areas relating to ecosystem services, to coastal hazards, and the marine economy. And these are all of course interrelated. But generally speaking, there is a gap in what global climate models can provide in terms of the information for this. They're not generally designed to operate either at the scales or with the processes designed to provide that information. So mapped on the right here, what the value chain is in terms of providing that information, going from from stakeholders through various communities of practice, illustrated by the coloured regions in this picture. And all I want to get into to convey here is that there are lots of different interacting components, so lots of different communities of practice, lots of different technical aspects to developing, at the bottom here, the actionable knowledge of future climate change in the coastal ocean. And in the FLAME Future Coastal Ocean Climates UN Decade Project, we're looking at seeing whether we can provide a better harmonized view of that value chain. And the benefits of this would essentially be able to provide sectorial and cross-sectorial global scale risk assessments. So looking at the scale of particular problems in the coastal ocean, building improved process understanding, and also building capacity in areas that are underrepresented. So the challenge is pretty big. So we started the global models, which even the highest resolution of the high-res MET models tend to be around the 25 kilometer scale on many a lot coarser. There are some examples of finer resolution for that. But then as you go down kind of a cascade of scales through the regional scale, where we tend to model at about 10 kilometers, to sub-regional about 1.5 kilometers, and then to local scale at maybe a few hundred meters, you see there is a really big cascade of scales that we want to translate our climate information down. And it's not just scale, there's also changing process interactions. As you get down to these finer scales, the interaction with the land becomes more important, and also processes like tides come into play. And also, we shouldn't forget that there's no single realization of the future climate. We are looking at multiple scenarios. We're looking at different realizations, both in terms of our model, what models produce, and also in terms of different societal visions of the future. So there's been an awful lot of work done in this in terms of regional downscaling in the world. There was an excellent paper by Liz Drenkard from 2021 on next generation regional climate projections, living with marine resources. And this figure from that paper here highlights the kind of added value that we'll be looking for to gain from regional downscaling. So on the left, we have 3 examples of global models, and on the right, 3 examples of regional climate models downscaling these, and so for primary production, temperature, and surface currents. And you'll see that in each of the downscaling cases, it provides new information that is qualitatively very different from what's provided by the global model. So lots of studies have done this around the world. We've mapped that in the by large marine ecosystem in this map up here. And you'll see that there's a great disparity. Some regions are very well covered, such as the Baltic. Other regions, such as East Africa, have few or no studies. So this is a real challenge in terms of actually how we can basically provide this information to places around the world. And that's the kind of thing we want to address in the FLAME project. So just drilling into detail about how we actually do this. So the straightforward approach, and the only available approach in a lot of areas without downscaling studies, is actually to directly use system models. And particularly if we're interested in marine ecosystems, these are generally limited to 1 degree resolution. They have multi-centennial spin-up, so tend to have difficult biases. So the present tends to drift. The conditions tend to drift quite away from present-day realities, and they're also very expensive to run. So it's difficult to run in small research projects. So the most straightforward approach to this is to take a regional ocean model and to use the output of the global model to force the regional model. This is comparatively cheap and easy to set up. You can run multiple scenarios. If you want marine biogeochemistry, you're then limited by the to the coarser resolution system models rather than the maybe higher resolution climate models for global forcing. And of course, any biases in the atmosphere and the ocean in that forcing model then propagate into the region model, and there are various approaches to correct that. So an evolution of that is actually to run a global model, a global ocean model forced by the by now it could be a global climate model. So you remove that, the restrictions on the choice of driving models, and you can then run multiple scenarios with a much higher resolution global model that you could use in the coupled model. You can correct for the biases, but in this case you're then out of balance in that you're not in dynamic balance with the atmosphere anymore, and that may introduce things like deep water mass drift. And then of course once you've done that, the global simulation, you can cycle down through regional models onto it. Another option is to introduce high resolution atmosphere downscaling, so example from the Cordex project. Or finally, what might be seen as the gold standard is to have coupled regional atmosphere models. So you see there's a whole range of possibilities and approaches that can be taken in this. Within the FLAME project, we're looking towards developing a global coastal ocean model and comparison project. So something might be called GCO-MIP. To actually make this as accessible as possible, we're proposing that maybe having 3 strands of activity in this. The first strand is actually comparatively straightforward, but even in itself will be a big step forward, and that is introducing common metadata, assessment, diagnostics, and best practice approaches that would be shared around a community of modelers. The next strand would be to provide standard model experiments, so particular choices of global models to provide forcing, common simulation strategies. And the third strand, which is possibly quite a big ask, is actually to have standardized regions. So regions that we say that actually if everyone could run this region, then we could provide a common assessment, for example, of uncertainty on it. But I appreciate that is generally quite a big ask for communities to work in regions that they would not normally do. So that's the outline plan, and it's very much a draft thinking at the moment. And we're moving towards evolving this and refining it through a set of protocol development workshops, most likely virtual. There may be some opportunities for hybrid or in-person meetings. And we would separate these into maybe 6 different themes covering different aspects of the problem, because as you appreciate, there's an awful lot of different things to cover here. So we'd have to cover those 6 aspects, and then bring the output of those workshops together into a coherent protocol, which can then be shared with the community. And we may well use the Coast Predict General Assembly in February as either a vehicle for some of these workshops is most likely, given the timing. So that's all for me. I'm quite happy to take any quick questions on the presentation, which if you put them in the Q&A, then I can answer them in the Q&A. But I suggest for time we move on to the case study presentations now. I'm just going to quickly skip back to remind myself who was going to go first. I think Georgia, you're going to go first. So I will stop sharing the screen. And Georgia, if you want to share your screen, the floor is yours. And I'll wave at you in about 15 minutes time.
Great. Thanks, Jason. So I'm going to share my slides and let me know if you can see them. Yeah.
Yes.
Oh, thanks. So again, good morning, everybody. My contribution today will be to tell you about an activity we performed during the Adriatic project. This was a cross-institute activity, so I listed here all the colleagues who contribute to this work. So what we did basically within our project, we performed a dynamical downscaling exercise in the area of the Adriatic Sea basin, and we aimed at answering the question that I highlighted in red. So we asked ourselves if a sub-regional to coastal canal downscaling can improve the current knowledge of the Adriatic climate. So I will focus a bit on the methodology that we follow, and then I'll present you the scientific results. And to conclude, I will give you some take-home messages, some ideas also we are thinking on the future project, which is AdriaClim Plus, so the follow-up of AdriaClim. So as Jason already told us, the new generation climate downscaling is progressing rapidly, and there are several both statistical and dynamical approaches that have been used and are going to be further developed in the future, as well as there is an increasing number of processes, multiphysics, multiscale processes that are going to be solved by the new generation climate downscaling. There are still some challenges regarding computational cost, data storage cost, regarding the number of processes that are still neglected or highly parameterized. And FLAME is among the initiatives that are underway to reach these goals. And under the umbrella of the FLAME initiative, there is the AdriaClim project that I'm going to tell you in detail, which was a 3-year project ended last year, while now we are in the phase of the AdriaClim Plus, which is the follow-up Interreg project. So what was our downscaling strategy? Basically, what we did, we performed a dynamical downscaling over a limited area, which is the Adriatic basin, with a double nesting approach. A first nesting phase to reach the sub-regional scale, a second nesting phase to reach the local coastal scales. Our dynamical downscaling system is a multi-model system. It is nested into an existing regional climate model available under the MEDCORDEX initiative. And there are 6 modeling components within our system, which are the atmospheric, soil, and hydrology components sharing the same computational grid, which is a big higher than just the Adriatic Sea. And then a second computational grid focusing on the Adriatic Sea is shared by the other 3 modeling components, which are the marine hydrodynamics, wave, and biogeochemistry. Then I will tell you a few words on the second phase of nesting that we perform to reach the transitional area, in particular the estuarine areas. So what is the novelty? We tried to solve a higher number of multiphysics and multiscale processes, including nonlinear interaction at the interface among the Earth system component. Among them, there is the reverse interaction that I'm going to tell you in detail. In fact, one of the assets of this downscaling system is represented by the hydrology component. It is based on Wolf Hydro code, and it basically allowed us to prognostically solve all the catchments which surround the Adriatic Sea, which are huge number, make the Adriatic Sea a dilution basin. And we reach a quite high resolution in time and space, 1 hour time frequency and 600 meters horizontal resolution, which is 10 times higher than the atmospheric and then surface component. This hydrological component is quite demanding in terms of calibration, so we performed a huge calibration of all the catchments. And we, as I put here in the panels, we calibrate and validate the basin cumulated rainfall and the reverse flow at the river mouth. And we were able to reach quite a good performance by comparing with observation, by comparing with the fast analysis, which was our benchmark. And this at the end can make then the hydrology climate projection a trustable product. We performed 2 time slice climate experiments covering historical range and mid-term future up to 2050. And the first step was to evaluate the performance of our limited area climate downscaling. So we focused on the historical range and we compared with available Copernicus reanalysis. So here I put as an example on the right side, 3 panels showing sea surface temperature, mixed layer depth, and sea surface salinity, every year represented by our limited area climate system, which is in blue, the driving regional climate model, which is instead in green, and finally the reanalysis, the Copernicus reanalysis we use as a benchmark. And we could demonstrate the added value of performing this additional step of climate downscaling, in particular looking at the capability to solve the stratification of the water column. Our mixed layer depth is lower than the driving regional climate model, but much closer to the available reanalysis, and the same for the salinity, which is lower than the driving regional climate model, and again, it fits better the available reanalysis for the Adriatic area. So looking at the main scientific results, let's start with the land-sea interface. Our climate downscaling, the climate projection we performed with our climate downscaling system tell us that by 2050 we should expect a decrease of the total river release into the Adriatic Sea of about 35%, with differences among the catchments. So here are reported as example the Po river discharge and the Neretva river discharge. All the catchments are found to decrease in terms of river runoff in the mid-term future, with the highest decrease affecting the catchment ending on the western side of the Adriatic basin. So the decreasing runoff can be explained as a direct consequence of the decreasing cumulated rainfall over the catchment surrounding the Adriatic Sea, and also decreasing relative humidity over the same area. So here are reported briefly the 4 seasonal panels showing the seasonal changes between projection and historical range for both relative humidity and cumulated rainfall. The other complex interface to solve with and to look in detail with our climate downscaling is the air-sea interface. So here are the top 4 panels refer to the seasonal changes of the latent downward flux, which is the opposite of evaporation, over our area of interest. And what we found is that the downward flux, or equally the evaporation is expected to increase through all season and across the whole basin. The same quite homogeneous behavior is expected for the sea surface temperature, again through all season and across the whole Adriatic basin. While looking to the changes in terms of the sea surface salinity, it is also expected to increase, but with in a quite heterogeneous way, with the ice effect in the northern part of the Adriatic basin and along the region of freshwater influence. So to judge the combined effect of increasing temperature and decreasing salinity across the Adriatic basin, we finally look at the Brunto-Vaisala frequency, the maximum Brunto-Vaisala frequency at the top 100 meters of the water column. And this is a way to judge the combined effect of salinization and heating affecting the Adriatic Sea. These 4 additional panels show that the stratification is expected to decrease throughout season just in the northern Adriatic and along the area, the major area of freshwater influence, meaning that the salinization effect is expected to prevail on the heating effect. While in the southern Adriatic, the heating effect can eventually prevail on the salinization effect, and the stratification can increase a bit in winter time and also partially in springtime. So there is this combined effect of increasing salinization and heating of the Adriatic basin, which we decided to investigate more in deep, look at the all water column. So we focus on the analysis of density stratification through the whole water column, and by distinguish between Northern and Southern Adriatic. And this analysis is reported in the two panels on the left column. And then on the right column is the dense water formation, again for the Northern Adriatic at the top and Southern Adriatic at the bottom, the right panel. So the message here is that looking at the Northern Adriatic, we found that in the midterm future, this density stratification is expected to decrease through all the water column, and also the density water formation is expected to significantly change and to increase in the midterm future as a direct consequence of the river decrease and evaporation increase. The changes in the Southern Adriatic are a bit more complex in terms of stratification. It is expected to decrease again also in the Southern Adriatic till 200-meter depth, while looking at the intermediate to deep water column, the stratification in the projection range is expected to increase. And this in turn means that looking at the dense water formation, instead what we expect for the Southern Adriatic, differently from the northern part, is a decrease of dense water formation. So the message here is that in the Northern Adriatic, the future change in terms of stratification and dynamics can be explained in quite a straightforward way in terms of decreasing river release and decreasing evaporation. So the buoyancy budget at the surface is expected to drive the density stratification and the dense water formation, while in the Southern Adriatic, the future change in terms of stratification and dense water are a bit more complex, and they can be explained as the nonlinear combination of multiple factors, including the changing river release, but also the evaporation and the heat loss at the Earth's interface, jointly also with other external forcing as the water entering through the Otranto Strait. And focusing on this last mechanism, so the water exchange through the Otranto Strait, these panels show the seasonal changes in terms of salinity at the zonal transit for the Otranto Strait, where the Adriatic Sea meets the Ionian Sea. And this panel confirms basically that salinization is expected through the whole section, with the only exception of the typical area of entrance for modified Levant intermediate water, which are salt water coming from the Eastern Mediterranean Sea, which are instead expected to decrease with this freshening effect that you can see. And this basically means that there will be a decrease in one of the main forcing mechanisms of dense water formation for the Southern Adriatic. So all these changes in terms of stratification and dynamics affect the total sea level projection. These additional panels show again the seasonal changes that we expect by comparing projection and historical range in our downscaling experiment. And these four panels in particular refer to the only mass components of the Adriatic total sea level, which is basically explained in terms of what are the water exchange at Earth-Sea length interface and water exchange through the Otranto Strait. So looking at the water exchange and the volume fluxes at Earth-Sea length interfaces, these are basically positive defined because there is they are defined in terms of precipitation, runoff, and evaporation fluxes. But we expect a decrease of this volume flux entering through Earth-Sea length interface. And we also expect that the net outflow, which characterizes the Otranto Strait, will decrease. So the net outflow is also confirmed over our projection range. It will decrease with respect to the historical range, but not enough to compensate the decreasing volume flux at Earth-Sea length interface. So at the end, this means that the mass component of the Adriatic total sea level is expected to decrease in the midterm future. However, if we add the steric effect, which is basically the additional term in our total sea level equation, which is conditioned by the temperature change and salinity changes, the resulting total sea level for the Adriatic Sea change sign. So we should expect a sea level rise through all season and also through all basin in the midterm future, with the only exception of the Northern Adriatic. So this is a quite new result that came out by this limited area downscaling we performed within Adriatic project, and the main message that came out is that the steric component, so the thermal expansion of the water column, the Alin contraction of the water column, they play a key role with respect to the sea level rise in the future of the Adriatic basin. And we can identify also a key role of the runoff decrease, which basically have a sort of modulating effect with respect to the sea level, the total sea level expected in the northern sub-basin, where most of the river release is located. When we look at these results, we have also to keep in mind that here we are not including the subsidence effect. And we know from the literature that it is expected to play a key role with respect to the sea level rise in the Northern Adriatic. It could explain up to 50% of the sea level rise in the Northern Adriatic. So if we add also this additional effect, the relative sea level rise could be positive also in the Northern Adriatic. Anyhow, what do we want to stress, to highlight on the basis of our downscaling experiment is that this dynamical downscaling demonstrates the spatial variability of the Adriatic sea level rise, and also indicate a slowdown in the future trend of the Adriatic sea level rise. This is a quite a new result with respect to global and regional climate models, to what is basically to what are the results of the state of art of regional climate modeling. And this is a quite expectable result if we consider that we are able to reach a very high resolution and we are able to provide a more comprehensive representation of the local water cycle. The second question is if we can trust this new result. And what we can say is that there are some recent evidence of an heterogeneous behavior of the sea level rise across the Mediterranean Sea, which basically go in the same direction of our results. These panels in particular are taken from a jointly work by University of Bologna and CMCC, which is based on satellite altimetry and reanalysis data collected for the last 3 decades. And what came out from this analysis is that in the last 3 decades, the sea level rise across the Mediterranean Sea show a quite heterogeneous behavior with a key role of the steric component. So this basically make our projection quite promising, at least. The Adriatic multimodal system include also, as I mentioned at the beginning, a biogeochemical component. So we provide climate projection also for the biochemical tracers. And we analyze the results by distinguishing 6 ecoregions on the basis of the trophic conditions among the Adriatic sub-areas. And the main message that came out from our climate downscaling is about a general oligotrophization of the Adriatic basin, which is expected in the midterm future. And it is particularly evident in the northern estuarine coastal area. So it can be explained, partially explained with the decreasing river runoff and the decreasing river loads. So this decrease in primary production, oops, sorry, I stopped, it was my mistake. Okay, let me see if I can. Okay, I apologize.
That's okay.
Okay, but we are close to the end. So I open again the biochemistry projection.
That's right.
Okay, so here the message is that this scenario in terms of oligotrophization, warming, deoxygenation, and acidification of the Adriatic basin tell us that there is for sure a challenge in the near future to consider with respect to the Adriatic food web and with respect to the resilience capability of the Adriatic ecosystems. And to conclude, I want to mention the second level of dynamical downscaling that we performed over the Adriatic estuarine areas. So basically what we did, we nested an estuary box model within our limited area climate system. This estuary box model is forced by the hydrology component and the marine hydrodynamic component of our multimodal system. And it is a quite a powerful tool because it basically solves all the processes that occur within the estuarine areas in an analytical way, but it is also extremely powerful in terms of CPU cost and data storage cost. So it is quite suitable for performing climate projection. And as an example, here are the results that we got for the Ofanto estuary, which is a shallow, extremely shallow estuary with an extremely low runoff regime. This estuary ends into the Southern Adriatic Sea, so a microtidal sea. And looking at the projection of the salt wedge intrusion length and salinity, we found that there is an expected salinization effect with a particularly strong increase of the salt wedge intrusion length. And also there is an expected increase of salinity at the river mouth. What is interesting is that in summertime, when we expect the highest increase in terms of salt wedge intrusion length, we also identified the lowest increase in terms of river mouth salinity, which is actually not something, which is not a contradiction. If we consider that it is an extremely shallow estuary, so it is extremely sensitive to the sea level rise. And the main effect of the sea level rise is to promote the estuarine stratification, which means that salt ocean water can intrude more inland while maintaining fresh water outflow at the top. So to conclude, some of the insights we got within the Adriatic project and with our sub-regional local climate downscaling. First, we found that this local climate downscaling allow us to capture the variability of the climate change impacts in time and space, which can differ from the results of global and regional climate models. Among the strengths of our downscaling strategy are the time and space resolution that we were able to reach, and also the multimodal approach, which basically allow us to provide an integrated representation of the local water cycle, and it is found to strongly affect the results in the Adriatic stratification and dynamics. There are still some gaps in the downscaling strategy that we aim to face in the future. It is about the quality of the available regional climate forcing and also the availability of the data in terms of data storage capability, which limit the accessible data sets. Then there are still issues regarding the computational cost and the downscaling jumps between the driving and downscaled modeling system. And finally, I would mention the processes or the interaction that are still neglected in the downscaling chain. An idea for our discussion is about the downscaling protocol that could be very useful. So defining common strategies, best practices that should be followed by the climate community. I want just to mention, if I have the time, the specific.
Well, I think sorry to cut you off there, Georgia.
Okay, thank you.
It's super interesting work, but I do think we probably need to kind of move on to the next presentation.
Sure.
Yeah. So yeah, really sorry to cut you off there. But please, any questions for Georgia? And I think that is really fantastic effort there in the Adriatic. Any questions in the Q&A, and we'll pick those up either during this or directly after. So Clotilde, should we move on to your presentation?
Yes, thank you. So now we're going to move to the Southern Hemisphere and talk about the Great Barrier Reef. So before I start, I would like to, I'm just moving your window first, so you're not in the middle. All right, so I would like to begin by acknowledging the traditional owner of the land that we're calling from and meeting on today, and pay my respect to the elders past and present. And for me today, I'm calling from Tasmania, Lutrawita, Hobart, Nipaluna, and this is land of the Muwinina people, and I'd like to pay my respect to their eldest. So today I'm going to talk about the dynamical downscaling approach for the Great Barrier Reef. So we're moving in the Southern Hemisphere on the east coast of Australia and the Western Pacific area. So most of the work I'm going to present today is actually a work of two postdocs, Jody Schlaffer and Lachlan Phillips, and they're also part of the ERIF team. So this work is sort of the contribution of CSIRO to the FLAME project that Jason introduced. And in Australia, in our kind of project world, it's part of the ERIF project, which is an information platform that is based on observation, modeling, but also informatics, and focusing on the protection and the management of the Great Barrier Reef. So the ERIF project's been there since 2012, so it's been around for more than 12 years, but we only started to look into climate downscaling recently, although it's very important for management of the Great Barrier Reef. So before I go into the downscaling, I'd just like to step back just for one slide about what the ERIF system is. And that's sort of our modeling setup there. We've got a 4-kilometer grid, so that covering part of the Coral Sea and also most of the Great Barrier Reef and the shelf area. To be able to drive this hydrodynamical model, we need atmospheric forcing, open ocean forcing, river forcing, and tidal forcing. So when we do a hindcast, we're trying to use our best forcing possible, and usually we're using reanalysis. And in this case, we're using the Barra reanalysis in the atmosphere with 12 kilometers. For the ocean, we're using 10 kilometers with BRAN 2020 reanalysis. For the catchment model, we are using the SEDNet and source catchment model from the Queensland Department, and we're using the TIDE for TPXO. And when we think about the climate downscaling, we were trying to find products that we could fit to this kind of benchmark here we've got for the hindcast. So when we think about our climate downscaling, we had some challenging opportunities there. And in a sense, we wanted that to fit with the time frame of the management of the Great Barrier Reef. And also we wanted a product that allows us to assess the major threat to the Great Barrier Reef. So in terms of time management, we actually have a lot of plan in place from the Queensland government and also the federal government. And the time frame is really 2050. So that was sort of our time frame that we have to keep in mind. We want to have a tool that allows us to inform those plans. And usually they update those plans every 4 or 5 years. And we want to, assess those risks. So the first one, of course, is rising water temperature and coral bleaching. And with this in mind, we have to think about the ocean circulation in this area. And really, we've got those south equatorial current coming in and bringing the climate signal from the Western Pacific with it. So we really wanted to have a system that can represent all those jets, those 3 jets that are very important to bring the signal all the way to the shale break. When we get to the shale break, those currents, depending on their position and their latitude, they're gonna change the connectivity among the different reefs. And that goes to the second point here. Those chronostaffing arch break, or when we look into coral larvae connectivity, those one are really important to set up the system. We also have very important water quality issue in the area. And that's, you can see it here in the title of those plan, water quality is big. And we've got 64 river boundary with flow and 101 with nutrient input point. And we really want to be able to represent that into the future. And what we have to keep in mind here is that actually we've got a wet season and a dry season. And those river floods that we get are very intermittent and sporadic, and that's those events we want to be able to represent into the future. And here it's a pretty animation that show you how, when there's rain event, how the water is propagating through the catchment and going all the way to the sea. There also is idea that, we're probably going to have more severe cyclone, and in our system, it means we need to be able to represent this type of weather. So that's the atmosphere there, this kind of weather condition that are very important in terms of wind and ocean circulation, and that's also going to be key for the resuspension of sediment. So with all of that in mind, that's the sort of strategy we went for in terms of which forcing we could use. And we went for the IRS MIP V1.0 from CIMEXIS in terms of atmospheric forcing and ocean forcing. And really here, we had to go for the high res of the high res MIP. And in the end, we only had 2 options given to us, CMCC CM2 and FGOES F3. CESM was another candidate, but unfortunately, we couldn't have access to all the atmospheric variable needed to calculate our SC fluxes, and we had to drop that one. And for the rivers, we didn't have access to a catchment model, so we decided to go with a machine learning technique and have a machine learning that would learn from the historical period and our best product, and then use the atmospheric field from the IRS MIP to create those new intermittent river forcing. So in the next few slides, I'm just going to go through a few very methodologic choices we went through, and I guess I wanted to do that to open the discussion afterwards. And the first one really was about time slice selection protocol, because we couldn't do the old 100 years. It was way too much for us. The importance of evaluation and assessment of your boundary condition. So in this case, those 2 models, CMCC and FGOES. How we handled the future forcing data through bias correction and dedrifting and other tricks. And just one slide with a few sneak peek of the result. So further time slice selection. So here it's just to put those models into perspective of the larger CIMIPSIC ensemble. And here we're looking at the global average near surface temperature. And you look at the evolution, and those, high-res MIP, they go from 1950 all the way to 2050, which is good enough for us, especially in terms of management. But they are, those high-res MIP, they are following the SSP5, so the 8.5, which is usually said to be, one of the more catastrophic type of scenario. But when you look at where our models sit in this ensemble, they actually sit quite at the bottom of this yellow pack, and they actually sit right at the ensemble mean of the shared scenario and number 2, which is the 4.5, which is deemed to be the more realistic. So we actually have 2 models, CMCC and FGOES, that do follow, in a sense, closer the multimodal mean of the 4.5. Then to select our slices, we decided we could do 10 years time slices, And how we decided to pick them, we actually followed one of the IPCC key metric, which is around this 1.5 and 2 degree warming in the near surface air temperature. This is kind of the big key metric that have been used out there. And so if you follow that, this is sort of the time slice we came up with in terms of fitting these 1.5 and 2 degree warming. So they're quite different with the different models. And we also made sure that those 10-year slices, during those we had the same amount, or tried to get the same amount of El Niño and La Niña event. So we really have a 1.5 warming that is sort of the trend. And same thing for the coral sea temperature anomaly, because there's a bit of a lag between what's happening to ENSO in the Central Pacific and what's happening in the coral sea. So we sort of did a mix of that to identify those 10-year slice time period. That was sort of the protocol we've put in place there. Now let's have a look at and do some evaluation of those RSMIP in the coral sea. So here we're looking at a section at 162 degrees east. And this is where a section that is cutting through the North Vanuatu jet, the North Caledonia jet, and the South Caledonia jet. And you can see here that's the reanalysis and showing the position, the green patches of those current, and where they are in the three RSMIP here. So they are represented in there, but they can be shifted a bit, especially in terms of latitude. And if you look at the salinity profile, there is a maximum subsurface maximum salinity in the coral sea, and it's well represented in brown in the reanalysis, but the climate model had some biases in there. So the next step we did is we went to try to bias correct those errors. And so to do the bias correction, the technique we followed was the one described in this paper here, the time varying delta from Pozo-Bilt et al. 2021. In that paper, they sort of split everything in three quantity. You've got the variability, you've got the mean, and you've got the trend. And in that paper, what they did is that they only kept the trend from the CMIP model or from the GCM, and they used the variability and the climatology from a reanalysis. Here, we decided to only keep the climatology from the reanalysis and keep the trend and the variability from the GCM. So here, that's an example showing the section of velocity along our boundary, which is here for our GBR4 model. And we can see those South Equatorial jet, but also the Gulf of Papua current that is going around here and going back into the Solomon Sea here. And you can see here our analysis, and here that's the two models we wanted to use. And there's a bit of biases in terms of the intensity of this Gulf of Papua current and also the position of the South Equatorial jet. And this is what you get when you correct them. And so we used monthly climatology bias correction using 10 years of the Brand ocean reanalysis. We did the same thing for the salinity. So here you've got spatial variability along our boundary. So which means that along that boundary, we just plot all the grid cell, all the vertical profile of salinity along that boundary. And you can see the mean position for Brand. You know, there's not a lot of variability around spatial variability, but there were quite a fair bit in F goals. That's for January and February. And that's the profile you get when you finish this bias correction, only correcting for the monthly climatology. And again, we were using 10 years. When you go to the wind, it was also important to do a bias correction of that wind. And here that's an example showing the monsoon trough. And the position of that trough is very important because especially on the continental shelf, the ocean currents are going to be driven by the wind mainly and the tides. And so the position of that monsoon trough gonna tell you how the connectivity is going. Is it going north or is it going south? So it's very important to have this monsoon trough in the right spot. To do this correction, we also follow the same methodology. Also, we keep the variability, so the weather and the trend from the GCM, but we used daily climatology with a 20-day rolling average. And we played a lot with that until we managed to basically get rid of the weather inside the daily climatology. We also do ocean dedrifting. So one of those, biases, I guess, of those climate models that they can be drifting, especially when there's not a very long spin up, which is the case for the high-res MIP, because it was very expensive to do a very long spin up. And here you can see in the control run, they have the drift in salinity. And so we use which is a well-known technique. We followed that technique to drift the salinity, but we had no drift in temperature inside the coral sea, so we just only did the drifting on the salinity. Now going to the river forcing, this is where we did the machine learning technique. And so what we really wanted, and here I'm showing the Burdekin River. This is showing the wet season and all the different years, showing that some year there's no flood at all, and some year there's some big spike, and they can happen whenever. So we really wanted to be able to reproduce this very intense flood event and intermittent event. So what we did, that is our step-by-step, I guess, recipe for the river forcing. First, we did daily aggregation of the GCM precipitation per catchment, and that's the example here. We've got the precipitation. We can see the catchment of the Queensland area here in the background, and we average the precipitation or aggregated all precipitation per catchment. Then we had to bias correct those precipitation, especially over the land, there's strong biases. So we did a bias correction of the time series per catchment. Then they become the input for the TCM machine learning model. So here that's showing you what we get out of the TCM. So this is for the Fitzroy River. In green, this is the observation during the historical period, and the big orange one and the spikes, that's what the machine learning give us for this whole period using the GCM atmospheric condition. Again, once we got that, we had a fourth step, which we're doing a bias correction of the river flow time series again. And we did that because you can compare the distribution during the historical period with what you get with the machine learning. And what we found is that you can see that in the distribution, we had too many dry days in that time series. So we readjusted it so it fit better the distribution during the historical period. And I just have one slide to show some results. Here, this is just a result showing the coral sea warming. So using all those models, and you can see that we've got a strong warming in the first 200 meters and a cooling subsurface. And sort of all the models tend to agree, except the intensity and amplitude of it changed a bit. And this is the warming for all those, 1.5 or 2 degree warming of the near surface air temperature. So that's really those IPCC key metric here we're following. If you look at the GBR warming, what we can see is that here there's a map of warming between those two periods. And we can see that spatially, we can see that the upwelling area along the shale break counteract the climate change signal. And that's where we're getting at now into analyzing the result. We're looking at, do we have the same amount of warming everywhere? Is it the same as where we've got coral reef? And in effect, we actually have less warming when we look at the location where we do have coral reef. So that's sort of the area we're going to look into now, more into details, to do some science with that climate downscaling. And that's sort of the summary of all the different downscaling choices we've made up to now. So we had to go with the IRS MIP, but there were just a few that we could use in terms of our need for our 4-kilometer models. We went with machine learning for the rivers, and we did some bias correction, dedrifting, and that's us. So for now, we just have hydrodynamical modeling, but with the ERIF, we actually can do also zoom, which hopefully we do that in the near future, going to 1 kilometer, maybe estuary or relocatable model. That's sort of capability we've got already in place. And we also can go all the way to the BGC if we wanted to. But at the moment, we just really at the beginning of the journey, I guess, for the climate downscaling, and that's where we're up to. Thank you.
You're muted,
You're still
Jason.
muted.
Thanks, Cathilda. That's great. Do you want to stop sharing your screen there? So we're now moving. We've got half an hour of discussion session now. We prepared a couple of discussion questions, and I'll quickly share these. I'm not sure whether people on the Zoom are going to be able to join interactively in this. It might be nicest if you could.
Jason, just to let you know, I shared the Google, the Drive, the document we prepared in the chat, so people can put their thoughts there if they want.
Okay, thanks, Anna. So the 4 questions we came up with. I mean, first, we're happy to answer any questions on the presentations, and those are very welcome. The 4 questions we came up in terms of developing best practice in this space is you know, do we see a benefit for a more coordinated activity in this, and how can we improve on that? Kind of what are the opportunities and challenges you see in it, and how best to organize it, how to make it happen. So does anyone in the Zoom have any particular thoughts or questions on this? I'm going to stop sharing these. I mean, I appreciate there's quite a lot to take in here, and it might be something to take away and think about. But any immediate reflections?
To me, it seems, following Clotilde's presentation, that it is a difficult task. And it seems that different groups have developed their own methodologies of how to choose their atmospheric forcing, of what's the preference? Should we go very high resolution? Should we look what is better in our domain? So, and how to correct every bias. So I think that a bigger coordination to start maybe standardize some of these choices would be useful for everybody.
No, I agree. I agree that I think the choice between high resolution climate and standard CMIP, I think is a really tough one. Yeah, because of drift and bias issues there. Yeah. So I see Yuri has asked a question in the chat to you, Georgia, about the river modelling. I don't know whether you want to answer that online.
Yeah, I can see it. Let me see. Yuri, you are referring to Yuri's one, right? Okay, so question on the biochemical projection. Does the warfighter provide the nutrients? The answer is no. It is only hydrology, hydraulic modeling. So what we did with our biogeochemical component, it is forced for sure by the warfighter runoff in terms of volume flux. And then the river chemical inputs have been initialized by Copernicus reanalysis. And then we exploit the relationship that we know between the river discharge and the nutrient roads. So the decreasing river discharge reflects into the decreasing nutrient loads. But this is something that we want to exploit and to develop further in the future. So in the new upcoming project, the idea instead is to add a module also for the river nutrients, which means that as we did with the warfighter for the runoff, also the nutrient loads will come out from a river nutrient modeling system.
Brilliant. Thanks, Georgia. So I'm not seeing any further questions or discussion points. If that's the case, then I've got a couple of final slides just on another thing, so I'll quickly share those. So the last thing I wanted to say was to mention that the Flame project is not the only activity in this direction emerging. So coming out of the World Climate Research Programme and their CLIVAR and Cordex activities through the Ocean Model Development Panel is a task group that is being considered to cover future climate regional projections, and we're probably familiar with Cordex as providing atmospheric regional projections, but this would look at how we can improve the regional ocean components of those. So obviously this has a lot of synergies with what we're doing in the Flame UN Decade projects, and there are we're aware of these overlaps, and myself and is involved in this, and Angela Mellet, who is from Mercator Ocean, who is leading this activity from the ocean side with the CLIVAR MVP, is involved in Flame as well. So you may well see the community invitations to participate in this this kind of sister activity in terms of future climate downscaling. Okay, I'm not seeing any further hands or invitations to or questions in the Q&A, so I suggest we draw it to a close there. I mean, the last thing I would say, that if anyone's interested in getting involved in either Flame or the Coast Predict program that Flame sits in, the door is very much open. If you just drop me an email, then I'm happy to kind of link you in with either of that, or there are QR codes on your screen now where you can find out a bit more about these. So I think there's no further discussion to be had, so I will draw it to a close then. Thanks very much for joining. I hope you found this interesting and informative, and kind of welcome any further question and dialogue on it, and then have a nice rest of your day. So I'll
just to
there.
mention that the Google Drive will stay open. So please, if you have any thoughts that you didn't share while we had this meeting, you can go there and add any comments that you have, and we'll collate them all together as a kind of report.
Brilliant. Okay, thanks everyone, and thanks to our speakers.